Industrial control systems and supervisory control and data acquisition system security seems to be an emerging security area. 5 years ago, 10 years ago, you never would have heard anybody talking about ICS or SCADA in a traditional computer security domain. But what we're finding over the course of, again, those last 5 or 10 years, the way ICS and SCADA systems are merging into the traditional IT world also means that security of ICS and SCADA systems is merging with security of traditional IT systems as well. So what is industrial control systems? Well, in their most basic form, it's a combination of hardware, software, mechanical devices that control a certain process or function in some type of automated way. And these are typically industrial applications. Industrial processes are increasingly relying on computers for automated monitoring, automated response, as a way to control the costs and a way to control safe operations, making sure that you take the human out of the loop. In theory, the computer can do a better job of maintaining safe operations because there's no room for, or there's no possibility of human error, except for where the programming goes wrong. But that's beside the point. And so you have this, complex system of, again, hardware, software, mechanical devices that are operating usually pretty sensitive or critical infrastructures. And they simply, the computer systems, the automated systems, can simply do it faster than a human operator can. They're less prone to error and therefore purportedly more safer than human-controlled systems. And so what this is commonly referred to as operational technology, or OT. You contrast that with information technology, or IT. In production environments, you'll see, or manufacturing environments, you'll see there are usually two different types of systems. And each system has their own group of people responsible for maintenance and security of it. So on the manufacturing side, inside the plants where they actually do the manufacturing, you usually have an OT network. And you've got system administrators in there, you have integrators, you have vendors, you have security people, but they're responsible for that plant network. On the other side, inside the corporate center, you have information technology, IT networks, system administrators, security people. And what we're starting to see is it's not distinct. It's truly distinct as it once was. You're starting to see a blending of those two areas where operational technology is using the internet more. It's using traditional IT protocols like TCP/IP. And so it's blending the OT and the IT world together. ICS has various functions. It's usually there to monitor the state of a process, whatever that might be going on, through sensing and measuring. It could measure whatever process that could look at whatever process it's measuring, compare it to a set of thresholds to determine, are we good, are we bad, and based on what it is sensing, take some type of action to either mitigate the risk of something bad happening, return the system to normal operation again, or in the worst case, absolutely shut the system down so that you protect life, limb, property, or the integrity of the process or the product itself. Consider a pipeline system that you're pumping, let's just say, oil through. You probably will have various industrial control system processes there to monitor flow, pressure, let's just say flow and pressure because I can't think of anything else right now. Just flow and pressure. And so your ICS is going to look at those and say, are we within norms? If we're within norms, great, there's a big green light that stays on. But the second that we overpressure the pipeline, the red lights go on and sirens start buzzing and the control system starts looking at, okay, where is the overpressure coming from? How can I shut that down, limit the damage that may cause, or do I need to shut the whole thing down because this thing's ready to blow up? There's a close correlation between control systems and critical infrastructure. If you look at the various critical infrastructure sectors of nuclear power, water, wastewater, oil and gas, mass transit, assembly lines, chemical production facilities, HVAC systems. There's really very few critical infrastructure areas that don't use some type of industrial control system. And so there's a close correlation between these two. And so you see, especially when you start talking about critical infrastructure like nuclear power plants, there's a very high focus on the security of these systems that are used to control these types of facilities. There are different kinds of building blocks that go into industrial control systems. The first one to talk about is a process control system. And it's usually very localized, but it's a system within a plant, facility, or operation that is used to control the control system, as it were. There are PLCs, programmable logic controllers, and these are the most atomic building blocks of ICS. They can do all sorts of things. That's why they're called programmable. You can program them to do quite a few different things. But generally, they're atomic because they're looking at a particular function or a particular process. And they're monitoring it. They may end up controlling it as well. And they originally were created as a solution for complex hardware problems or increased, high cost things that just weren't robust enough to survive out in the wild. Because typically you'll see PLCs out in the environment. They're usually not in hardened bunker facilities like you might find a PCS or some of the other elements of an ICS. These are usually out in the field. And so they're usually pretty rugged. They're better suited to the environments that they work in. And they, for very simple processes, the PLC may be it. This might be the only part of the control system that there is. Two related devices, the remote terminal unit and the master terminal unit. These are what control physical or mechanical objects such as pumps, switches, might be responsible for transmitting the state information or whatever the PLC is sensing. The RTU may be responsible for transmitting that information back to the facility. And actually, it will communicate with the master terminal unit on the other side of that link. This could also be called the system controller, but it's there to monitor the inputs from the RTUs, basically handle communications with all the remote devices, and provide some type of interface for the operator to send messages or at least see the data from all the RTUs and PLCs that are out there. There's also a notion of distributed control system. This is an architecture where you've got multiple PCS, multiple process control systems, or multiple master terminal units. Anyway, you're looking at multiple components and controlling them all from a single supervisory controller. And so as an example, let's take a look at our hypothetical pipeline operation here. Horrendous drawing of a pipeline, but let's just go with it. So in here, you've probably got some kind of let's just call this a gate. Down here, you're going to have some type of programmable logic controller, or PLC. That's going to control that gate, or it may have sensors in it to detect pressure, temperature, flow, whatever through this pipeline. And so that's the PLC's job. Now, the PLC isn't going to be able to communicate with anything. So what it's going to do is have a connection to some type of remote terminal unit, or RTU, and that is going to communicate with some type of master terminal unit. And the master terminal unit is probably going to be connected to some type of process control system. oversimplifying greatly. But here you've got a PLC doing your sensing and your monitoring. You've got your RTU transmitting information, what the PLC is to the MTU, and then you've got some type of control system here that is displaying this information to an operator, making decisions on whether to keep the pipeline operating or not. And it will communicate back to the MTU, who will then communicate to the RTU, who will then instruct the PLC, keep the gate open or shut the gate because this thing's about to blow up. Then, what you might have is multiple copies of this. And all of this becomes your distributed control system. So where you've got multiple pipelines, multiple PLCs, multiple RTUs, multiple MTUs, multiple process control systems. All of these might be, in different cities. Like, let's say this is LA, this is New York, this is Dallas. You might have a distributed control system that's looking at all of these individual cities and their pipelines and controlling the flow between all of them if they are interconnected. Now, add one more layer of complexity or confusion into this, if you will. Let's talk about supervisory control and data acquisition, SCADA. It's another type of system that allows you to collect and process data from these multiple sites. So it's a way to connect various sites together and monitor the data and control the devices that are there. So you usually see these with widely distributed systems that require a lot of human intervention. You'll see these in pipeline operations. You'll see these in electric grid operations. And it is distinct from a distributed control system. However, the lines between these are very, very blurred, kind of like the IT and the OT concept. Because a DCS, a distributed control system, is very similar to a SCADA system, sometimes the terms are used interchangeably. I'll go back to the camera here and just add that the SCADA network will usually go through some type of HMI or human-machine interface. And so if you really wanted to simplify things, add an HMI block here, and now all of a sudden this whole thing is your SCADA system. So in graphical format, in much better representation than what I could do with a pen and paper, you can see the various components here of the system. You've got some type of mechanical field device up there in the upper left, communicating with a remote terminal unit. All of these come down through either some type of proprietary closed network, or they could be using open networks like the internet or wireless systems, or even phone mobile operator systems. So you probably have multiple mechanical field devices, multiple remote terminal units. All of those are communicating with a master terminal unit down here that has some type of control logic in it, is presenting things to an operator either through SCADA software or through some type of HMI. And then you've got all of these PLCs up here. I should have mentioned that here in the black box. You've got all these mechanical field devices that are communicating through a PLC to the remote terminal unit down to the master terminal unit. And this is really where challenges start to occur because traditionally the PLCs or the RTUs used proprietary communication paths. Sometimes they were dedicated paths, discrete lines. Now what we're finding is that a lot of these devices are starting to use regular open networks, internet paths, mobile data connections, that sort of thing. And that's where the security implications come into play. So again, historically, these control systems had security through obscurity. Nobody knew what they were. Nobody understood the proprietary protocols that ran over them. They had protected communication, dedicated lines, point-to-point lines. Everything was isolated. This is changing. It has been changing for the last 5 years or so, and it's just going this direction where you have the operational technology landscape shifting into information technology. So what was traditionally OT is now traditionally IT. And it's where those things start to cross is where you start to have security concerns. So the PLCs or the RTUs using TCP/IP, that's a big change from what it was 10 years ago. But it means that it's now using an open standard. A lot more people understand TCP/IP. A lot more attackers understand TCP/IP. And they're able to craft attacks against devices that use this. Things like running over LANs or LAN protocols, or open wireless networks, or even encrypted wireless networks. The fact that it's using a 802.11 AC or N or even a 4G LTE network is leaps and bounds more open than what it was in the past. And because of that openness, we're starting to see security issues with it. Again, this convergence between the two means that all of the traditional vulnerabilities and security issues that we used to see on traditional IT networks are starting to show up in what are now operational technology networks. So the fact that your control system might be tunneling through the internet to reach the control system or the monitoring station, the fact that it's tunneling through that could introduce issues. Because traditionally, the control system networks here were always considered to be real-time systems, meaning if there's any type of delay in this communicating with the HMI or process control system or anything like that, that system now has a weakness. It has a vulnerability. If a PLC over here is starting to detect an overpressure on the pipeline and it can't communicate back with the process control server, which is going to say shut it down, what happens? So it's these types of concerns where historically these were really not so tolerant in terms of timing. It demanded I need to be able to communicate with my process control server. And if I can't do that, then I've got a problem. But when you start mixing these network technologies and we start writing over open networks, you run the risk of not being able to support real-time communications with denial of service attacks and that sort of thing. So it's opened up this big landscape of attacks against control systems that we hadn't seen previously.